Thank you all for attending this session where a team from Raptor Engineering and myself will present the secure FPGA-based BMC. It's a very interesting topics, BMC with security combined together. Uh, to talk about myself, my name is Bunir Ahmad. I'm the complete architect. I have been working at Lattice for a few years now, but prior to joining at Lattice, I worked at various industries and companies. I had more than 20 years of system architecture experience designing various storage and server system. Some of them are basically purpose-built server, application-specific server, as well as standard OEM general purpose servers as well. Right now, I'm mainly focusing my time on looking at FPGA need in server space and driving the strategy and growth in the FPGA in various segments of the servers, various e-commerce servers, and matching together both architecture as well as functionality. Let me go to the next slide, team, please.
Yeah. So my name is Timothy Pearson. I'm a computer engineer at Raptor Engineering. Over 20 years experience, hardware, firmware, actually from system level design all the way through HDL, firmware, and kernel work. I am the product lead for our open power lines. These are secure, fully open firmware systems built on the Open Power ISA. If you're familiar with RISC-V at all, Power is an open ISA along the same lines, but it's standardized. And there are multiple moderate and high performance offerings available that are compatible with the Open Power ISA. This work is actually what led us into designing and developing secure soft BMC solutions using the Lattice products.
Okay. So the agenda slide, so the way that we set it up is the first we like to look at what BMC or baseband management controller is. And then we like to do a little bit deep dive on what is the data center remote management has to do with BMC. And then our main topics is that, what are the security challenges that we see in the BMC? And then what is, if you have to design a secure BMC, what is the core requirements for that? And then we have some examples here that FPGA is BMC that is already exists in the market today. And then the last slide is basically the key takeaway slides, what do we learn? And then we'll have question and answer after that. So let me go to the next slide. So BMC as of today, right? So today BMC is based on SoC with all general purpose server functionality predefined. So if you look at hyperscalers, storage servers, and others, typically they do not build general purpose servers anymore. There's more application-specific servers getting built. For them, a fully featured BMC just will add cost. It's not only the cost, because if you have functions that are not needed, it basically adds debug time, security holes. For example, I have a few examples here that the VGA connector add cost, and hyperscaler may not use VGA because everything is done remotely today. USB port obviously can add a security risk. Again, in typical general purpose servers, you see that, but in application-specific data center servers, do we need it, right? So the bottom line is that the BMC comes with many not needed interfaces that also add security holes. And with that, the bring up, debugging, validation are time consuming. Another thing is that today, if you look at the BMC, it's pretty much the closed architecture. It has closed bootstrap code. So any debugging can take significant amount of time because finding with with the reason for the issues is difficult, right? With everything is closed. So duplication of an issue can be important. So bottom line, with the constantly changing the data center need and the landscape, and people are designing with more and more specific application-specific compute, ASIC BMC that has full functionality, all the legacy interfaces, legacy hardware, may not be suitable for, especially for data center guys. Let me go to the next slide. So data center remote management. So one of the key functionality of the BMC is remote management. I like to bring up the remote management because That's the doorway of a server or platform to the outside world. And obviously, that's add in security, right? Anything that you have an access, anything that you have an outside access, the hackers can access. So this is the remote management. Just like to understand a little bit more. So remote management is a key feature that BMC for that. So for the BMC perspective, if you look at here on the left side, pretty much each server has a BMC, or each node or chassis may have a BMC or multiple BMCs. But BMC is basically goes through a switch, and that a remote management servers. It can be multiple hardwares or softwares, depending on how big the management domain is, that manages this servers through the switches and to the BMC and go to the server itself. So what's happening today is that, if you look at on the right side, data center has thousands of servers, right? And then that's the BMC is enabling this remote management of servers. And the key thing that BMC does is, which is a uh, big task, is that the hyperscalers, there, if someone rents their rack to a, some vendors, some customers, they do they need to do update the OS once they get the rack back, right? And even that, they will have regular OS updates, firmware update. They may need to install new applications, and none of the thing is done today uh, by going to the server itself. So everything is done by remotely. I have an example here. Let's assume that you want to update the OS of the servers. What BMC would do in this case, BMC will create a virtual DVD drive, and then you can shut down the system, the platform itself. By the way, BMC never shuts down, even if the server can be shut down. So BMC will basically create a virtual DVD drive. So next boot up, BMC can boot up, the server can boot up from the DVD drive, and OS update will happen. So BMC has essential functionality. That's very key thing that, and not only the OS, but any kind of firmware update, any kind of peripheral firmware update, everything is done through the BMC, because that's the whole management port that the data center server has. Some of the other functions that just like to mention here is the fault reporting. So BMC basically keep tracks on the health check on every single component of this platform. It does the fan monitoring, fan control, temperature monitoring, health monitoring, presence detect, all kind of management functionality that you can see BMC does. It also has IPVM, which is the a multiple keyboard, mouse, video support capabilities. So these are the key things that BMC does today. So let me go to the next slide. So BMC role in a cloud. So this is the animation, slide. So just like to go one by one. So if you want to do what is the BMC does, as you see on the left side, which is the platform or server, which does host I/O. Now, host I/O is typically workload I/O, storage I/O, network I/O, and then you have BMC. So BMC itself is a separate entity within host. So this itself is its own computer. It has its own power sequencing. This is its own operating system, reboot firmware, all those things, application. So BMC itself, in all practical purpose, is a separate entity within host. And then if you go to a little bit more, so if you look at here, you can see that the BMC has its own power sequencing. You can see server host its own power sequencing, and that's how we manage to make sure that BMC can be server can be powered up without the BMC turned off. And this is a very interesting and very essential component from the data center perspective, because they want server to be turned off, but not the BMC itself, right? Because BMC manages the server. It basically it has the capability of turning on and off the server. From the BMC perspective, this is the things that it's a hardware layer. It has pre-boot firmware. It has operating system layer. As you can see, it has application services. It's for itself is its own computer. And if you look at some of the things that BMC does, is definitely BMC manages servers. It does fan presence, LEDs, fan sensor management, LEDs presence through an LPC. But it also has a PCIe that takes a video from the server, and then that has the main thing that it has that you can see here. For any kind of management, it provides the pipeline. There's an Ethernet connection, the management I/O connection, which is not the same as the workload I/Os, This is what the pipeline it does that actually helps the data center cloud management and basically gives an access from outside world to the server through the BMC. So this, in a nutshell, how the data center cloud management works in the BMC in a very high level view. So let me go to the next slide. So this slide, team, I want to introduce, I want to ask team if you can, team, please present this. This is the Open BMC architecture, team.
Sure. So as you might be aware, there's a software stack, actually in a complete application solution called OpenBMC on the market. This has been adopted by a number of ODMs at this point, IBM, Western, Qantas, and Raptor Computing Systems, among others. I think Google's also been contributing to it. This is a Linux-based BMC solution that currently targets the A-Speed hard BMC ASICs. It does make heavy use of D-Bus and similar application level, system level technologies that are available on the Linux platform. That said, there is nothing in the OpenBMC architecture that specifically ties it to the A-Speed SoCs. So one of the things that we are actually investigating right now is the feasibility. There's actually been some initial studies done on this, was the feasibility of bringing the entire OpenBMC stack onto the Lattice soft BMC products using Kestrel. We actually did have a proof of concept a couple of years ago on that. But this is specifically the architecture of one of the OpenBMC solutions, named confusingly OpenBMC. And I will be differentiating between the concept of an OpenBMC and the OpenBMC software stack at various points through this presentation. But OpenBMC stack itself currently basically makes use of the hardened cores, the hardened peripherals that are present in the A-Speed SoC. And as a result, that hardware has actually contained various vulnerabilities over time that have inadvertently compromised the higher level OpenBMC stack. There are a couple of CVEs that are probably available for that that had to be patched out. But at the end of the day, the OpenBMC stack is all about implementing what was on the prior slides. That is to say, communicating with the host, communicating with the outside world, pulling in all of the sensor data, making decisions about how to drive fans, what actions to take on the system, doing your system event logging. Depending on your host, it might even be more involved in the boot process. Certain hosts require that the BMC provides firmware over either LPC or eSPI to the CPU. Usually there's some sort of debugging functionality built in. Where we do run into limitations on a hard ASIC versus a soft FPGA is actually when you start getting away from whatever interfaces are specifically hardened in that flavor of the ASIC. So at the bottom, at the hardware level here, you can see that we have things like SPI flash, and there will be other blocks in there like LPC. But what happens if you need to talk eSPI and the ASIC doesn't support it? Well, you have to bit bang over GPIO. You've just taken a multiple orders of magnitude performance decrease over, say, an FPGA-based or soft HDL-based solution. So this is more of the general system architecture. We actually have an alternate OpenBMC that is not the OpenBMC stack in the Kestrel system that actually uses a Zephyr RTOS. And in that, we have a similar architecture on the bottom, the hardware and bootloader kernel. But in that case, we have a small native bootloader, and our kernel is actually the Zephyr RTOS. And then we have our application sitting on top of that. There are a couple of different solutions available depending on what you actually need, what your attack surface is, what kind of size of the BMC you want. Obviously, if you're looking at OpenBMC as in the OpenBMC stack, you can see that we're using Linux and D-Bus. This is a fairly large application when it's finally compiled down to Flash. It's 16 or 32 megabytes, and you can. It's a very full-featured system. It has all your IKVM, everything. But at the end of the day, very similar to what we were talking about earlier, it may actually provide too much functionality, too much attack surface. So this is why we have two completely different stacks available at this point in time, depending on the exact requirements. And then Munir, if you wanted to.
Sure.
Okay.
So let's talk about some of the loan security challenges of the BMC. So as you say in the previous slides, the BMC is, it's a system itself. It has a lot more buses, a lot more interfaces, and then so if you look at the existing security challenges that we know, the hyperscalers, large entities, KSPs, they provide service to their customers, right? And some of the customers, they handle very mission critical data. It can be their financing data, it can be their banking data, it can be their human resources, their compute need, their storage needs. So also that if you look at the credit card system, PO system, so they need something that they can basically require zero trust solution. So some of the existing BMC today that has trust us, right? That has some of the closed boot ROM or pre-boot format that is closed to trust us. It may or may not work for some of the hyperscalers, right? The same thing is also some other issues that BMC has. BMC execute is very BMC is a very privileged, system, within a system, right? It does all this privileged operation with the hardware and for memory access. So BMC security is very important. It cannot be, it cannot be hacked. Same thing, the configuration parsing, because if you want to do some kind of configuration changes on the run, that can definitely enable attackers. And BMC does this all the time, right? Uh, Also, the configuration, if you're changing the configuration on the devices, you're adding devices, some of the security settings like HTTPS, KVM encryption, they can enable the weak IPMI modes. Again, as a security hole. There is also can be settings that control logging functionality that can allow attackers to say some of their sensitive logs they can get into, or they can turn off the fans, things like that. So all these things is basically telling us or showing us that there's a lot of security challenges that we have in the BMC today. And by the way, there are some even is some of the security issues are known that in the industry today for many years now that may need architectural changes of the BMC, and that's not possible. You don't. There's no way you can change a BMC and hardware and a system. So these are the challenges that we see. That definitely, is one of the key concern from the industry. So what is the core requirements? What is needed at a minimum, right? This is the slide. So we know that BMC needs to be secured, but what exactly that mean? And this is a very high level. So obviously we need to support secured boot. We need to support secure configuration. We need to support attestation. And one of the key things is root of trust for security. Now, all this root of trust and the meanings may be different from person to person, right? Because root of trust, the security landscape itself is very widely from people to people. It's not something that is one size fits all or one definition to all of us. So that is a big questionable, definitely, that what you mean by root of trust. So that's, and from an FPGA perspective, the root of trust itself is a configurable root of trust, because there may be always a security risk, and a programmable hardware can actually address those kind of security risks. Next, we need to have minimal attached surface, right? If you have a BMC that supports, so modular functions is the key one. If you have a BMC that supports all the legacy interfaces, that means you're adding more security holes in the system. It's the first thing is it's an unnecessary, obviously. You may or may not need those functions. And the second thing is that obviously, like adding or validating those interfaces can add time. If something is unnecessary, the validation may not be complete. That is definitely a concern. The other thing is that flexibility should be applied to the build time. Now, granted that there are some options that you can turn off on the build time, runtime, but we need to have the BMC the way that we want, right? If you want three functions, you want BMC to have these three functions, not turn off those two functions in the runtime. BMC needs to have external verification of the BMC image prior to allowing the BMC to load. This is something that we also say firmware resiliency, but that is something, it's a different topics. But in a nutshell, we need the BMC to have, and someone else, a third party, to verify the BMC image, which is somewhat done today. And the last one, this is a very important one, is that BMC should never fail. Because if the BMC fails, what that means is that someone has to go physically access to the servers and take care of that, right? So there's a lot of things that BMC is a work on, and that's something that in a nutshell, we don't want that, right? So this is the core requirement of secure BMC. So that, let me go to the next slide. So if you look at the FPGA-based BMC, um, I think, Tim, you want to talk about that? Because you have that ECB5-based BMC.
Yeah, so we do have the Kestrel stack, which when I'm referring to Kestrel, it's actually an entire solution based on open HDL that Raptor Engineering wrote for its own product lines and then released. It's based on open tooling, open firmware, and right now the Zephyr RTOS-based BMC solution running on top with the alternative open BMC stack-based solution in development. So as a bit of background, the reason that we actually went with an FPGA-based BMC for some of our product lines, we actually saw issues coming up. So we use the AST2500 from ASPEED on some of our existing power systems. And the 2600 plus require proprietary ASPEED boot ROM. Now, for our customer base, it requires 100% open firmware, and this would be some of the hyperscalers, would be some defense type applications, that sort of thing. In addition to other entities that's requiring full control and security, they're not going to be able to accept that proprietary boot ROM, especially with it in the path it's providing ASPEED's secure boot functionality. There's concerns there regarding bypass, there's concerns there regarding denial of service, who actually owns the device, etc. So we actually started to integrate our technology that we were developing for years, even prior to that, into the world's first soft BMC, which we then called Kestrel. That made its way onto one of our Power 9 platforms called Sparrowhawk. That's a very small embedded VPX form factor type device. And when we were developing Kestrel, we literally were looking at this from what we were running into issues with the open BMC stack on the ASPEED device. So a lot of that was coming from the complexity of the open BMC stack. A lot of that was coming from the ASPEED SoC itself. As I kind of hinted at earlier, vulnerabilities in various parts of the silicon. So we took more of a modular approach, both in terms of the hardware, in terms of the peripherals, in terms of the firmware itself. We actually decide what we need for any given platform. We can configure that, and before we even generate a system image, literally the FPGA image, we can decide what peripherals, what communication buses we need on that system, and tailor that to that specific platform. We don't basically, by completely removing what we don't need from the system, we've minimized the attack surface as much as possible, both at the hardware level and then also at the firmware level. Now, we do have a couple of products coming up. One is we have what we call the X1 BMC device that's actually built on Lattice technology, but that provides what we call an owner-controlled root of trust. And that's, again, based on soft reconfigurable logic. So you have full visibility, full control. When Raptor talks about security, our focus is primarily on one of the two prongs or the two paths for security. And our focus is on what we call owner control and open source, meaning that when we sell hardware, you have complete control of the hardware, complete control of the firmware and software running on the hardware, complete control of the tooling, the HDL, etc. And then there's a second prong, which I believe we'll be going to kind of later in this presentation, which is for entities that are not capable of managing that level of complexity or have no desire to manage that level of complexity in their stack. So we are aware that security means two different things to kind of different audiences. But as far as Kestrel is designed more around that whole concept of control, of visibility, of auditability, of modifiability, and the ability to modularize the system, configure it the way you need for your data center, deploy it once, and not have to go in and patch a bunch of security holes in systems you're not even using. So the root of trust technology I was talking about, that's providing external verification. It's authenticating essentially the BMC itself to the external data center operator, or to, maybe not even to the operator, maybe to you in a completely different location, maybe your control systems, however you want to configure that. And then I guess the final thing is, the interesting thing is with the Lattice FPGAs in particular, the Lattice designs are very energy efficient. So we're looking at comparable power use to the hard ASIC for very simple, basically I would say for superior functionality depending on the exact use case. And we do have this solution in the form of what we call a mod BMC card, similar to the Run BMC form factor. We're actually working with the Run BMC guys to try to update the standards and bring it into, basically bring the standards up to modern levels. But that's using a Lattice ECP5 device. It's got integrated DRAM, integrated Ethernet, and it's essentially a BMC card. Very, very small solution, and that is actually shipping today.
Okay. Next slide, team.
And this is actually showing that the card we're talking about here. So there's actually two things. The top right, you can see the SODIMMs, DDR4 SODIMM physical form factor. Obviously, electrical signals are very different, but that's the BMC on card using the ECP5. There's 1 gig DRAM on there. It's got HDMI integrated. It's got the internal BMC flash. It's got Ethernet on board. Literally everything you need. You feed it 5 volts power, and it does the rest. This is actually an isolation of the original Kestrel system that was integrated into our Sparrowhawk system, which is shown on the lower right-hand side. That's the OpenVPX card that has no hard eSpeed or any other hard BMC ASIC on board whatsoever. It only contains the 2 FPGAs that provide the BIC and the BMC functionality for the platform. And if anyone's familiar with IBM Power, this is not a trivial exercise. Unlike Intel, unlike AMD and ARM, where you basically kick off an internal management core to start the boot process, we have to talk to the CPU over something called FSI, which is basically a form of high-speed JTAG, very complex protocol. We offload all of that to the hardware, the soft logic inside the FPGA, which means we can reach line speeds over FSI, which you cannot do with the hard ASIC, the 2500. The functionality simply doesn't exist. So it's a kind of a great example of what we can do. But then we also have to serve the firmware over LPC and manage a whole bunch of other things in the boot flow. So to do all of that, we have a combination of internal soft logic. We try to bus master wherever we can, basically let the soft logic do its thing without CPU intervention as much as possible. But we do have a full power compliant soft CPU inside the Kestrel stack, and that allows us to run the Zephyr RTOS, and would also allow us, with a little bit of development, to run the OpenBMC formal OpenBMC stack on top of the Kestrel HDL solution. One of the pain points that we've run into with HP with OpenBMC, the former OpenBMC stack, is the boot time. With the power systems, because the BMC is so tightly integrated with the boot process, we have to wait for the BMC to be online and ready to perform all of these boot tasks before we can bring the host online. It takes 3 minutes to boot a hard 8-speed ASIC into OpenBMC. And that's a significant delay. When you plug the system into power, you have to wait 3 minutes before you can power on the host. So one of the things that we were doing when we were modularizing and making everything as minimal as possible is we can bring this thing online. When you apply standby power, we are up and running in under 5 seconds using the Kestrel stack on the Lattice FPGAs. So we do have some initial support for network protocols and things on top. There is further development that needs to be done, primarily because we did choose Zephyr. Zephyr needs a little bit of work in terms of the HTTPS protocols. There's reports on that. But that's one of the reasons why we also want to be able to offer the OpenBMC-based or OpenBMC stack as an alternative on top to, again, within the open owner-controlled security track, to then further split that into extremely minimal, essentially system control functionality only type functionality, or open BMC with remote management and your IKVM and everything else on top. So we're actually looking at potentially 4 tracks, depending on what how you want to define that, between the 2 security models, and then within those the 2 call it application and kernel level security models. So there's a lot of flexibility in the solution, and we definitely understand that certain customers, say certain hyperscalers, are going to want the completely open solution. We understand some other customers may want the other solution, and within that, there are applications for the control only, almost you can look at it as a microprocessor almost solution, or the full application stack solution. We're also working on a third firmware, because one of the reasons we selected the Power soft CPU is because Power is a standardized ISA, very well established software support, very well established kernel support going back 20 years, which means we actually have the potential to treat the BMC as the little tiny system, complete system that it actually is. So one of the third options that we're working up is literally a Linux distro type model for the BMC, where you can modularly upgrade the software components the same way that you would manage any other host, instead of a monolithic image like you have to deal with today with OpenBMC. So we got a lot of exciting things coming down the line based on this technology.
Okay. Let me go to the next slide. So, thanks, Tim. So this is, I just gonna briefly touch about some other solutions. I'm not sure about how developed the solution is, but we have seen some proposal from Ant Micro about their BMC. This is the block diagram, and this is the dev kit for them. We didn't see exactly, as I said, that how ready the solution is, but I just like to show as some of the proposals that are going through from the FPGA-based BMC perspective. So let me take the next slide. So the FPGA-based BMC, so it's a complete solution that we see it. It's a security plus system management together. So as you can see that it certainly can support, as we have seen in Raptor solution as well, standard BMC functions. It is configurable as needed. But what it does is more about the security advantages, right? With an FPGA BMC, uh, hardware vulnerabilities is patchable via bit stream. You may not need to change the device itself. It's a programmable hardware. What is an ASIC? Sometimes you may need in your hardware. For FPGA BMC, we have a zero trust. There is no binary blobs, no closed tool chains or vulnerabilities to hide within. Device is fully under control of its owner, and this is what one of the things that team from Raptor is driving, which is zero trust condition made. So basically, the customer owns the complete tool chain, complete binaries, and all those things, and they can see what is inside of that, and that's the main driving factor from Raptor Engineering as well. But we also can do the PFR integration, and this is the value add that we see as well, because the post-quantum crypto capability is post-quantum crypto itself is changing, right? All the standards like across US, like NIST compliance, TCG, and even you go to the across the Atlantic, EU security councils, all those they're driving this PQC capabilities, and the specs is not finalized, things are still fluid. And I think this is something also the FPGA can tackle within the PFR integration itself, and something that we also in the discussion of looking into that. Can we integrate the PFR is part from a resiliency. This is something that NIST 800.193 compliance tools talks about, which basically gives the firmware detect, protect, and recover capabilities. So you can detect if there's hack happen, it can protect from any hacking happen, and in case if the hacking happen anyway, you should be able to recover it. So we can also combine this PFR integration of the PQC and then combine the BMC all together in one single package. The other functionality that you see, modularity, obviously, you can choose the function, the build time. If you don't need USB, you don't need USB. You just drop the USB IP during the build time, and there is no way USB can be enabled on that one during that time frame, right? So you don't, you can do on the build time, uh, and you can have this bare metal scenarios, right? You can have the FPGA can be the anchor of trust, because in this situation, FPGA is working as a hardware root of trust. So when the service rented out the tenants, you can still pull it back and be as a root of trust and it's still working as needed. And if there's any security transition happening from the system ownership, if you have a master key, you can provide the master key that ownership, and it's a safe transition from customer A to customer B, without any of the, because nothing is hidden here, everything is pretty much open. It's a zero trust solutions. So this is the same few things that we see. Let me go to the next slide. Some of the other features. Today, BMC does some kind of a verification uh, of the platforms, but again, uh, to be a real platform verifier or for attestation of peripherals, uh, you need an root of trust inside the BMC. And especially things happens today, especially on the dumb peripherals, right? There's no way to attest those dumb peripherals today because each of the peripherals works a different way. And even BMC cannot do this today. I think in the programmable FPGA, we can take a different approach there to have programmed this BMC to have the group these dumb peripherals and make some attestation there. Now, this peripheral attestation is still an evolving phase. There's a lot of discussion happening, and today, not 100% of the peripherals is attested. So that is something that we see FPGA can play a very important role. Again, centralized security policy can have FPGA-based BMC, and it can have a security domain that is separated from FPGA that serves in the chassis control, FPGA BMC, and FPGA BMC that can serve as a local control. You can have a different security policies there. You don't have to have the same security policy in a chassis and same security policy at the node level, right? That is something is possible there. Uh, FPGA can also be flexible for the cloud provider for control policies, right? If you want to have access to someone to certain areas of the storage devices, to certain areas of the system, that something can be done as needed. And again, everything is within the secure tool chain. You don't need to have manufacturer or ASIC BMCs, any special tool chain to support that. As Tim said before, it has better system control than traditional BMC. You have seen that, as the team was saying, that BMC can take up to 3 minutes to turn on. I think for a x86 system, for a storage system, I even seen like 20 minutes. It takes up to 20 minutes of BMC turn on because it has to go through all that attestation of the peripheral devices and all those things. You don't need to have everything up and running before can start the controlling the systems, like fan. You don't need to have BMC fully up and running before you can handle the PWM and the fan. And this kind of systems, you can easily do an RTL on the FPGA to control the fan, especially in the in a quiet system area like hospitals, education. That can be very helpful. You can have, we mentioned that flexibility and consolidation of multiple functions. If you look at today in the DCSM architecture, DCSM is basically doing separation of security and control and system management in a separate card, which is a DCSM card. And right now, we can easily combine LTP and PFR. So DCSM today has three different chip, right? One is for BMC, one is for PFR, one is for LTP. That's something we can definitely combine, as well as BMC can be combined as well together. Uh, so in a nutshell, I think the whole thing, when you have those things together, you're protected beyond PFR because all in include a system that can give you the complete security. It's a silicon level security, hardware level security that can go beyond protection of the PFR. Because if you look at the PFR, it only the application level, OS level, firmware validation, right? Firmware security. So also, I think it can also be a simpler board design. If you combine multiple functions, then the board design layers of the board can be much simpler. Okay, with that, this is my last slide. I just like to mention this because I think I just want to say another perspective of why FPGA-based BMC is important. So this is a OCP, High Performance Computing Subcommittee. This is the different design that is being approved by the OCP. And this is a very interesting, very unique architecture, because typically, if you look at any servers today, the data path is typically about 15-inch to 20-inch. And this particular architecture, the data path is few millimeters. So all the power loss that we have, everything is because the long transition of the data, long data transfer that's happening, and this is actually tackling that. This can take hours to explain, but in a nutshell, I think what the calculation shows is this kind of architecture. To move 1 bit of data today, we need 20 picojoule of power. This actually trims down to 1 picojoule. It's a 20 times improvement from the power consumption perspective. Again, this is a very fancy, very future-looking architecture. Nobody has this architecture. This is still a proposal, but I'm just showing that even in the future, this is probably a 5 years or 10 years from now. I'm not sure how long, but I just want to show even for that kind of future, we're still looking at FPGA-based BMC about in a reference architecture because of this flexibility, the programmability that FPGA has. Okay. With that, let's go to the next slide. Tim, you want to take the key takeaway?
Yeah. So obviously, the BMC's attack surface is forefront on pretty much everyone's mind. Anyone that has a data center with systems in there is fully aware of all of the issues. I mean, most operators are literally have segregated data planes specifically for BMC management. This is, to say the least, not using the technology to its fullest capability. So we definitely need better solutions that aren't dependent on just trust us hard ASICs, just trust us firmware components, especially when you're talking about potential compromise of the entire host, and with compromise of the host, compromise of all the application layer data. So we are working, obviously, on the Kestrel system to provide solutions to these issues. That includes owner control at all levels. That includes the second prong, where you're looking more at PFR, things like that, more of a vendor managed path for companies that are more familiar with that. But in all cases, reducing the attack surface where possible, trying to make it so that the BMC can be deployed once at hardware or bitstream level, and then updated modularly at an application level, maximizing system uptime, minimizing the attack surface, making it so that you actually could expose the functionality of the BMC in a bare metal hosting scenario, potentially to the outside world. And that would be a bit of a game changer, especially where zero trust systems are concerned, where the customer that's leasing the server wants to ensure that that particular machine is unmodified, not tampered with, basically non-malicious, either from a hosting provider perspective or from a third-party attacker. We do have, as Munir was mentioning, a couple of different devices that are coming out to support the two prongs. I mentioned earlier in the presentation the X1 from Solid Silicon. That's more of the owner control path, fully open everything under the owner's control. Or the other device that was just mentioned on the previous slide, more of the PFR solution. In both cases, there's a focus on trying to minimize your parts count, trying to move away from multi-chip solutions that are not only expensive in terms of design effort, in terms of board area, supply chain management, but also potential security risks from a direct physical access perspective. The more components that you have spread out over a board, the more points at which an attacker with physical access could tap signals, could modify signals, could attempt to inject faults. So in both paths, both security paths, we are moving toward a single chip solution versus a multi-chip solution that we use today. And Lattice and Solid Silicon, along with Raptor, are in a very, very unique position to be able to provide solutions to these issues. in both today and in the coming months.
And I just like to add to this. Yes, we can also see that, as Tim is saying, this need for a customer need for all elements of the BMC to be fully understood, and the all of the value proposition is that, definitely we can integrate other functional elements inside the BMC as well. So this is the key things that we see in FPGA to be a flexible, can add functions, uh, and definitely it's a zero trust solution. There is no black box. All this security that is needed from today as well as in the future.
I'd
Um,
like to just comment too that, on the previous slide, we may be a lot closer to that architecture than 5 or 10 years. I would estimate that we're probably 2 to 3 to having a Power 10 system using a lattice technology FPGA to bring it online. So there's, put it this way, it's much closer than 5 years. That's a long horizon, right? But I would say we're more like 2 years out for having maybe not this exact solution, but something that is leveraging the base technologies that we're talking about with Power 10, with the Kestrel stack, with soft BMC. So there's a definite stepping stone in the middle. You don't have to wait 5 to 10 years for the entire solution here to come to market if you want to start working with some of the technologies, especially in the OCP, HPM, MHS form factor.
Thanks, Tim. So I think what I mentioned by 5 to 10 years is that this are, you know, just from this block diagram perspective, yes, it's a 2 year solution. But this architecture is a perpendicular architecture. So typically, what you have here is that when you go for a standard server, you have CPUs and memories, everything in the one side of the board, right? This is a different architecture. This is actually through the board. So all this has is basically you have a CPU one side, BMC on the other side, and everything is just a card interface, which is how they reduce the data path from 10-inch or 15-inch to the few millimeters. So I think that technology is still, a talking way. But yes, you're right. From the FPGA perspective, BMC perspective, it's 2 years or less.
Yes, I would agree, and it's mostly just because um, it can look like we're talking about OCP solutions, on this diagram, right? Because we didn't go into a whole lot of details. This diagram is actually showing a number of things, and one
Right.
of them is just the whole concept of an OCP-based, like like an MHS type solution using the FPGA soft FPGA BMCs, using Power 10, et cetera. So I just wanted to kind of
Sure.
clarify that there's stuff that's going to be available in 2024 that's going to be leveraging some of this technology. 2024, maybe early 2025. So if anything, there's a very bright roadmap here, very bright future.
Again. But anybody interested in this, I think if you look at OCP, HPC architecture, reference architecture, I would encourage to do this is a very radical architecture, not from the BMC or this particular perspective, but the way the placement of these other components. But yes, BMC and as Tim is saying, we see this, is in 1 or 2 years time frame. So that's not a big, that's not far away. So with that, I think right now is a question and answer. So let me see what I have the question. The first question is that is a PFR not the sufficient for BMC security? What does the value add to your FPGA-based BMC? So if you look at the PFR is platform format resiliency. It's basically part of the NIST compliance 800-193. The PFR protects, detects, and recovers BMC operating system, right? And any application software. So this is an SPI-based solution. So if you have BMC operating system, your application, fan algorithm, all these things run from some Linux coding. You put it in a SPI flash, and the SPI flash is protected by PFR. But what is not protected in the PFR is, and which is what the secured FPGA-based BMC can bring into the equation, is that pre-boot firmware. the closed loop HDL, all those things that ASIC former ASIC-based BMC has today, that is not the PFR doesn't have access to that, right? That PFR only has access to operating system, application level system, or the Linux code on that. So that's what the value add that we're proposing. So that's what the thing that is adding on top of what PFR has, the secure BMC. Okay. The next question I see is that I think, Tim, this is probably something you can take it. You're expert here. How do you compare the soft processor versus hard processor?
So this is actually, it's an interesting question because it's going to depend so heavily on what you're actually trying to do with your platform. As a direct example, you're really comparing apples and oranges. I'll use Power because I'm familiar with it, having worked with it for so many years as a perfect example. So when we're actually trying to bring the Power host online, right, we have to read firmware over SPI. We have to feed it out over LPC. Now, on the A-Speed hard ASICs, as an example, we're using the CPU, and we're basically loading one of the cores. And on the 2500, you only got, what, two? So if I remember correctly. You're using that core at almost 100% just to shuffle data around, right? There's no bus mastering, there's no DMA, none of that actually works. So during the boot process in the Power 9, the CPU, the hard CPU inside the A-Speed 2500 can actually become part of the bottleneck as to how quickly you can bring the host online, how quickly you can shuffle the firmware bytes as required in random access mode to the Power host CPU. Whereas on the soft FPGA solution, we literally implemented all of that using DMA. So the CPU, even though the CPU is running pretty much an order of magnitude slower clock than the hard ASIC, because we're using the CPU just to command where the data is going and letting the FPGA logic actually handle the data path, the data flow, we can actually bring that Power host online even faster using the FPGA solution than we could using the hard ASIC solution, just because we have a more optimized data path customized to that particular host CPU and its particular requirements. So I guess at a very high level, the key takeaway I would have is that if your application is heavily CPU bound, if for some reason you are trying to do heavy computations on the BMC, which in my opinion is the wrong approach, that should be shuffled off to the host, it should be shuffled off to an accelerator, it should be shuffled to somewhere else other than a key security and control component. But if you're trying to do heavy computations on the BMC, you're going to need a high speed hard ASIC core, and you're going to have to put up with the issues that arise from having everything hardened. If you're using the BMC as a control component, basically how I would say is more intended for the platform, then you can offload almost all of the CPU intensive and especially wide data path type tasks to the FPGA soft logic and actually end up with a very comparable overall performance, potentially even with lower latency, because you're doing true multitasking, multiprocessing, simultaneous processing, right, in independent logic circuits, instead of having to context switch on a CPU between the various threads and mimic simultaneous processing. So it's really going to depend on your application. In practice, I have yet to see a well-designed BMC system that is purposely doing heavy computations on the BMC. So it's in my opinion, even though our CPU is an order of magnitude slower, it's offset by far by the ability to have all the acceleration logic built into the soft BMC hardware.
Okay, thanks, Tim. So next question is that, let me take this question. Can you do the big? How do you see the differences and how can you address it in the FPGA? So yeah, it's a good question. So if you look at the BIC or BIC or baseboard interface controller, what BIC does is a subset of BMC functions, and in many cases, typically it controls fans, monitors temperatures, does logging, system inventories, issues. It certainly so from the FPGA perspective, or even from the BMC perspective, it certainly is a much smaller lift than a BMC. So yes, an FPGA can handle the BIC, And if some system has two bigs, I don't see any problem by having multiple bigs combining to one single FPGA. That is also feasible, and this is also better than existing big ASIC based bigs, because if you look at all the bigs today is ASIC based and have a lot more functionality that you may or may not need, and this is what the FPGA can provide a value add. And again, sometimes there's no specification of the bigs, by the way, so it can be uh, the functions can be varied from platform to platform. Again, because the programmability of the FPGA, you can actually pick and choose the functions that are big. So you have to that advantage again to pick and choose functions. Okay. Uh, the other question I see is, can you have a BMC and other functions? Like what other functions you can do? Again, that is something that I believe is choice of how you like to design the FPGAs. It is BMC. What are the resources available? As Tim mentioned, that you do want to run acceleration in the BMC, or some things in the BMC that they want to do. But typically, it all depends on the user choice, right? If you want to run the particular functions, especially if I look at the DCSCM design, as I touched before, that if you just run LTPI, certainly that's an option. If you run just a TFR, certainly that's an option. If you want to run a small portion of acceleration for some sensor logging, that is an option. But again, all depends on what you're choosing, right? And being an FPGA, you can have multiple generations, multiple families of FPGA that has more resource or less resource that can be suitable for your design. Okay, I think that's the last question I see.